All right, so solutions and concentrations, right? So we've talked a little bit about solutions in lab, and concentrations are gonna be the units of the solutions that we deal with, right? And so in our solution, we usually have two components. We have the solute and the solvent, right? Our solute, how do we define the solute? Does anyone remember? Yeah, it's what's being dissolved, right? What is being dissolved, and it's generally going to be in the smaller amount of things. Right? It doesn't have to be, but generally it's going to be the smaller. And our solvent is going to be what?
What is being dissolved in?
What is doing the dissolving, right? What is doing the dissolving? And that's usually going to be in the larger amount, right? For example, we use sugar and coffee as an example. Sugar would be our solute, and then the coffee, the water in the coffee is our solvent in that case. And so one thing that may be a little counterintuitive is that solutions and solvents, right? So the solutions itself may be in any state of matter, right? So the atmosphere around us is technically a solution, right? It's a solution, it's a mixture of different types of gases, right? The most prominent gas in the atmosphere are going to be nitrogen and oxygen, so you can think of those as solvents. For the less common ones like hydrogen gas and things like that. But they can be in any state of matter solutions. Generally, when we're looking at solutions, we're looking at aqueous solutions, which means things that are dissolved in water, at least for our class. If you guys go on to organic chemistry, you'll also look at organic solutions as well. And so some examples, we have the air, we have oxygen, which would be our solute because it's in lower proportion to nitrogen. We can have gas and liquid, like a soda bottle. That's what makes it fizzy, is that you have carbon dioxide gas molecules dissolved in the water in the solution. You can have liquid-liquid solvent mixtures, like vinegar, which is acetic acid and water. And then you can also have solid things dissolved, like sugar and coffee, or salt in water as well, right? So these can be any state of matter. And so when we talked about solutions, we also talk about the idea of solubility, right? And what was the kind of expression you hear a lot in chemistry when we're talking about solubility? Usually there's 3 words, but this one I only have 2. It's the same word 3 times. It's usually like, likes, like, right? Like, likes, like. So like dissolves like. And what that means is that if you have 2 polar things, they will make a mixture with each other, right? So ionic solids dissolve in water because water is a very polar molecule, so it can help surround the charges in ionic solids. Oil and water don't mix because water is very polar and oil molecules tend to be what? Non-polar, right? But if you have oil and put it in a non-polar solvent like hexanes or gasoline, something like that, the oil will mix with it and you will be able to dissolve it, right? So if you ever get gum in your hair or something like that, and people put peanut butter and stuff on that, it's because the oils in the peanut butter will dissolve a lot of the organic material that's in the gum as well, because they share similar physical properties. All right, so ionic solvents because water is polar, like polar ionic solids. In non-polar molecules, such as oil and grease, dissolve in non-polar solvents, and something like hexanes is what you'd see. You guys used a little bit of hexanes. What lab was that? Was that last week? Remember, it looked like the dangerous,
Were the colors on it? I forget what it was.
I can't remember. I just remember the hexane container being in the. It was last week. We talked about miscibility of different liquids and stuff. I can't even remember what the lab was. But it was, hexanes was the dangerous looking can, right? And hexanes are dangerous because a lot of organic solvents tend to be very flammable and carcinogenic.
It was intermolecular forces.
It was intermolecular forces, but I can't remember what the actual lab It's itself was. TLC, that's right, it was a TLC lab, right? You made hexane solvents, right, which went up your thin layer chromatography lab, or your chromatography paper. And how good of a solvent it was for your solute molecules, which were the ink molecules in that case, determined how far it traveled along your TLC paper, right? Okay. And so when you have things that have different properties, it leads to the idea of miscible versus immiscible liquids, right? Miscible meant what? Does anyone remember? They mixed together, right? They mixed together. And if we were talking about intermolecular forces, what does that mean? If they mix together? Yeah, they form intermolecular bonds, right? These are like hydrogen bonds, right? They have similar intermolecular forces, is what we would say. They would have similar intermolecular forces. Let me write that neater. Intermolecular forces. And immiscible, then they mean do not mix together. And that would mean that we would have not similar intermolecular forces. Again, this goes to the idea that like likes like. Things that have similar properties like to stay with things that have the same properties as them. If they have different properties, polar and nonpolar, then they will separate. So here in dichloromethylene, that is a nonpolar solvent. Water is very polar, so those will not mix together. If we have a solution of iodine, that is a nonpolar solution, what can you say about the solution on the top there? What would you expect of this solution right there? How would you describe it?
It's immiscible.
It's immiscible, right? And what does that mean for the intermolecular? How would you describe it in terms of polar and nonpolar there? It should be polar because iodine is nonpolar, right? So whatever this is will be polar. And if we looked at the solution of nickel nitrate or nickel 2 nitrate, what can you say about the clear solution on the bottom? This would be nonpolar.
Wait, are they all mixed with water?
The iodine, those, I mean, it could be water, but there's a lot of clear solvents, so it's hard to tell. That one, right? I honestly, it's impossible to say, right? We can just say something about the properties of that solution. All right, so this is what it means for it to be soluble or insoluble in something. Does it dissolve in something else, or do the things mix together? So these would be liquid-liquid mixtures. If something is soluble in a solvent, for example, if it's a solid, that means that it dissolves in that liquid, for example. And so once we get things dissolved or things in solutions that are mixed together, we then quantify the amount of stuff that's in the solution with something called concentration, right? And so the amount of solute dissolved in a certain amount of solution is called the concentration. And usually it's defined as the amount of solute divided by the amount of total solution. And it's important I say total here because that's kind of easy to get mixed up in concentrations. Because it's not just the solvent that we care about when you mix things together. It's the total solution when you mix things together. So on the previous slide, we had test tubes. Let's say one of them is defined as the solvent, and the other one that's not mixed together is defined as the solute. The volume, or the amount of solution, is not equal to the amount of solvent. It's equal to the amount of solvent plus the amount of solute. So this is an important distinction here, right? So if, for example, am I good to go back? I'll let you guys keep writing for a second. If we're looking at one of those test tubes, see, you can write it here. Nope. I can't write it there. I have this one here. If we have one of these test tubes, right? This is solution 1, and this is solution 2. We say that's the solvent, that's the solute, right? right? The total volume is the volume of solution. And this is going to be important, especially when we talk about dilutions. The volume, or the amount of solute that we have, divided by the solvent, doesn't tell us about the concentration. It's the volume of the solute, or the amount of solute to the amount of the total solution. Liquids tend to not be compressible, which is why we use volumes in this case, right? If it's a gas, it's a little harder to define things in terms of volumes. And generally, the way we look at things, depending on what field you go into, if you're in the health sciences, mass or volume percent is usually how people will look at these things. So they'll say mass to volume percent, or concentration of an IV being delivered or something. And in chemistry, right, so if you stay in the sciences or the natural sciences, molarity is usually what you will see. And that's what we will be dealing with most, but we'll go over some examples of mass and volume percent concentrations as well. And so a mass to mass percent concentration is just equal to the mass of the solute divided by the mass of the solution times 100. Mass of the solution in this case is equal to the, oops, let me write this neater. Mass of solution is equal to mass of solvent plus mass of solute. Right, when we're thinking about percent calculations, percentages, we usually think the part divided by the whole, right? So in terms of mass, we have the part, which is just the mass of the solute, divided by the whole, which is the mass of the solvent and the mass of the solute. All right, so when we're looking here at our test tube, this would be the mass associated with the solute divided by the mass of the total solution. All right, so three different S words, right? Solute, solution, and solvent we have to keep track of here. If we're looking at a mass by volume percent, so this is the common one you see in the health sciences, it's the mass of the solute divided by the volume of the solution. And the volume of the solution is equal to the volume of solute plus the volume of solvent. In general, when you're looking at mass to volume, the volume of the solute tends to be very small. So for example, if you think about dissolving sugar in coffee, you add some grains of sugar, that doesn't really change the actual volume of your coffee at all, right? It stays relatively the same. So your solvent, it takes up the majority of the solution. This tends to be small for solid, liquid mixtures or solutions. Because the volume of the solid tends to be a lot smaller than the volume of the solvent. And then for a volume to volume percent solution, this is just going to be the volume of the solvent. Usually this is going to be for liquid-liquid solutions. So for liquid or gas solutions, you take the volume of the solute divided by the volume of the solution, where the volume of solution is equal to volume of solvent plus volume of solute. And you really only use this concentration when those two are relatively comparable to each other. And so the last thing, oh, Tiffany? Yeah, of course. And the last thing, I'm going to skip ahead a couple slides just to give us the definition of what molarity is, because that's one important for the lab today. And we'll just have a kind of chalk talk about it when we get up to lab. And that'll be the last thing. All right, am I good to go on? All right. And so for chemistry, I said molarity is going to be the concentration that you use the most. It's defined or usually represented by a capital M. This is going to be one of our units that we use in the class. And molarity is defined as the moles of solute over the liters of solution. So the units are moles per liter. So this is why we talk about chemical quantities before we get to solutions, because we have to understand what moles are, right? It's the same idea what we talked about those other concentration units, mass to mass percent, mass to volume percent, and volume to volume percent, except now we're expressing the amount of solute in solution in terms of standardized units as moles of our solute over the liters of solution, right? It's still the amount of solute in a certain volume of solution, right? So this is the important, or the most important unit of concentration that we'll be looking at this class. All right, I'm gonna